So developing new molecules is a difficult task. And this is in part due to the immense search space, which is estimated to reach around 10 to the power of 80 viable molecules. And then this combines with the high costs associated with testing single molecules that need to be synthesized and then tested in vitro and in vivo, with the costs of bringing even a single molecule to market reaching around $2.8 billion. And finally, also due to the nature of molecules, where a single change to an atom or to a functional group can induce large changes in bioactivity or on its toxicity profile. So all this makes the process of finding and optimizing new molecules very hard. There have been several computational methods that have been developed to help with this problem. However, an ideal method has still haven't been reached, where one which would readily output new molecules that would have the desired properties, would be easy to synthesize, and would also be really novel, so they would have no prior IP problems. So over the last couple of years, there's been some interest in applying deep generative learning to generate new molecules. There's been several architectures that have been explored, like autoregressive models, such as simply stacking multiple recurrent neural networks, or more advanced architectures like adversarial autoencoders or generative adversarial networks. In this work, and it's also a very popular architecture, we'll be employing a bare-dimensional autoencoder. Alongside the exploration of various architectures, there's also been some interest in exploring various molecular representations, or how to encode a molecule in the software and how to generate it. The most popular one has been to generate a molecule as a string of tokens, linearization of the molecular graph, as in SMILES. However, there's also been some attempts to directly generate the molecular graph, or even directly generate the three-dimensional molecular structure. However, there's no consensus in how to generate these representations, and in the meanwhile, SMILES-based methods have achieved very good performance, with even some instances of experimental validation, where the molecules were synthesized and then validated both in vitro and even in vivo to have the desired properties. So how exactly are we going to generate molecules with this method? So as I said, molecules can be represented as SMILES. So as you can see there on the top, SMILES is a string where each atom is represented by its atomic letter, and then there's some syntax tokens for representing rings or branches. This string can then be one-encoded or converted into a binary matrix, where each row represents an index in the string, and then each column of that row represents the presence of a specific token, where each row will have just a single one, denoting the token at that place. So we then employ recurrent neural networks to try to learn this representation. So during training, what we'll do is we'll feed the first row of this matrix and ask the network to predict what the next row will be. We'll then feed it the second row and ask it what the third row will be, and so on for the rest of the molecule, and then for the rest of the dataset. Once the network is trained, we'll use it in an autoregressive mode, where we'll start by feeding it a special start token. In our case, it was the token G, which was also added to the beginning of every molecule during training. So we feed it that token, and we ask the network what the next token will be. From that prediction, we then sample one token and add it to the SMILES that we are building. At the same time, that token gets also fed to the network again, and we again ask the network what the next token will be after these two. The network makes a new prediction, we sample and append it to the SMILES, and again feed it to the network. So the network will be operating on its own outputs, and we will be building SMILES in a sequential manner. So that gives us a way to generate molecules as SMILES. However, that still doesn't solve the problem of how we are going to generate molecules with some desired properties. So there's also been a large interest in the literature about this. Some methods employed transfer learning, where a model could first be trained on a large data set of molecules to learn to generate molecules, and then retrain on a smaller data set with molecules with the desired properties in the hope that the model learns that specific chemistry. Or with reinforcement learning, where the model can be directly biased towards generating those properties. The approach that we'll take in this work can be regarded as latent space navigation, where we'll be exploring the structure of an autoencoder, which is a network that's trying to reconstruct its own output, but crucially with a information bottleneck in the middle of the network that forces it to compress its input before reconstructing it. And so we'll then apply some optimization algorithms to try and navigate this latent space, which is usually just a reduced dimensional real number vector. In our case, is 128 numbers, to try and find those vectors that correspond with molecules that have the desired properties. And even in this regard, there's already been experiments using Bayesian optimization, gradient descent, or even already genetic algorithms. So, as our title suggested, we'll be employing multi-objective evolutionary algorithms to perform this search, which we believe that this is a good choice, as as optimizing molecules very rarely focus on a single property. So we almost never simply want a molecule that's very soluble, for instance. We usually want one that's bioactive to a specific receptor, but not active for another one, and then also easy to synthesize. So it's usually a multi-objective problem. So we felt like multi-objective algorithms would fare better. So we started by seeding our algorithm with a random sample of 100 molecules from the test set used to train the model. So we used the model's encoder to create an initial population. That population then gets reconstructed back into molecules using the decoder, which then gets scored according to the desired property. At this point, we have a population of individuals and also their corresponding fitnesses. So we can then employ the evolutionary algorithm, which will select and then apply its operators to create a new population and repeat this process. For the operators, we employ the standard one-point crossover, a Gaussian mutation with a 10% chance. So each element in an individual has a 10% chance of having Gaussian noise added to it, and also the same chance of having a random mutation drawn from that interval. For the evolutionary computation part itself, we leverage the JMentalPy package, as it already implements various evolutionary algorithms and they are already validated. For the single objective cases, which we'll use mostly as a baseline, we employed a simpler genetic algorithm. And then for the multi-objective, we employed the non-dominated sorting genetic algorithm 3. In the last case study, we will also compare this algorithm with 2 other multi-objective algorithms. So for the deep generative model itself, we employed a SMILES-based variational autoencoder, whose architecture was proposed by Polikovsky and his team. It's a recurrent-based architecture, so both the encoder and the decoder are recurrent neural networks, more specifically gated recurrent units, and this was implemented using PyTorch. The model was trained on 1.5 million molecules drawn from the Campbell database, and during training we employed loss annealing or latent loss annealing. This is to help the model learn, as a variational autoencoder has a 2-part loss. The first part tries to teach the model to reconstruct its input, in our case to generate molecules, and then the second part of the loss tries to give some structure to that latent space. Tries to regularize that latent space so it can then be easier to navigate using some algorithm. And however, during training, that's the second part of the loss is much easier to optimize. So the model can get lost and leave the encoder part out. So during training, we apply a very low weight to the second part, to the regularization loss part, and allow the model to learn to reconstruct its input, and only then we regularize it. We also employ teacher forcing, which I won't get into here, but it's also a technique to help the model learn the syntax that we want, in our case, smiles. And we also employed an early stopping of sorts, where we allow the model to train for 30 epochs and then shows the last one, which showed a significant improvement, which in our case was epoch 20. So we then applied our method to a set of case studies that have been commonly used in the literature in similar methods. So we started by optimizing for the drug likeness, which is a single score that combines multiple chemical properties into a single score again. And then we also optimized for the penalized solubility. We then constrained that same score, the penalized solubility, to be similar to a starting molecule. And then finally, we try to optimize for a bioactivity and at the same time for non-toxicity. Throughout these case studies, we'll sometimes also mention diversity. And we are talking about molecular diversity here, where we are measuring the average time-mode similarity between molecular fingerprints. And this gives us an idea of how diverse the solution sets are that our models are generating. For each case study, we performed also 30 runs to give us more stable results, with the exception of the similarity constraint one. So for the first case study, where we optimize for drug likeness, again, this is a single score. So we only employ the single objective algorithm. Nevertheless, we could saturate this score similar to previous works, where even our worst run could still find a very high score with 0.9475. As for the diversity, even the single objective algorithm could find very diverse solutions. As we can see in the bottom, those are the 3 best molecules. That's the results that we are reporting, and they are indeed very distinct molecules. So for the next case study, we then optimized what's commonly referred to the penalized solubility. So we are trying to maximize the water octanol partition coefficient, where larger numbers mean that the molecule is more hydrophobic. We're trying to make the molecule more hydrophobic, and then also penalize it by the synthetic accessibility, or how easy a molecule is to synthesize, where we want the molecules to be relatively easy to synthesize. And then finally, a penalty for unusually large ring structures, which again penalizes the molecule for unusual chemistry. However, as it has been previously noted, that this algorithm can be trivially solved using simple long aliphatic carbon chains. And indeed, our methods could find those chains. As you can see, all our 30 runs converge to this type of solutions with very high scores in the 30s or 20. However, if we look at the diversity of the solutions that we found, we can see that the multi-objective algorithm found much more diverse solutions than the single objective, where the later one always converged to the same exact molecule in all but one of the runs, which wouldn't give us much to work with, even if these are trivial solutions. So next, we performed a rather more interesting case study where we optimized for the same objective, but this time we constrained the optimization to finding molecules that are similar to a given starting molecule. And this is a more realistic case, as in drug design, they will often first find the lead molecule, one that has the desired bioactivity, and only then try to optimize that molecule for some property. So we perform this optimization for a set of 800 molecules, and then report the success rate, or the percentage of those molecules for which you could find a molecule that both improves the score and also satisfies the constraint. And then we did this for 4 different constraints. It's worth noting that the improvement that is being reported is only with regards to the successful cases. So only methods with similar success rates should have their average improvements directly compared. So with that said, we outperformed all baselines for the first 2 thresholds, the easier ones, where we could attain a very high success rate, nearing 100%. However, it's worth noting here that the zero threshold is the same as the unconstrained case, and we again find those trivial solutions. Then for the 0.4 threshold, our success rate falls between Branson et al. And Mazerk et al. Work. However, we still find a better improvement. And lastly, for the higher threshold, where we must find molecules that are very similar to the starting molecule, our success rate falls slightly below that of Mazerk et al. However, we still find a better average improvement. And then on the bottom, we can see the best improvement that we found for the highest threshold. And we can see the starting molecule and the optimized molecule. And the changes are slight, but they are there, and they are significantly improving the score. So another aspect of this case study is the diversity of the solutions that we are finding. And we again, from the top table, can see that our methods are falling mostly in line with the baselines, and that again, the multi-objective case mostly is outperforming the single objective in this regard. Then on the bottom, we have a plot of the number of generations that it took for each threshold. So due to computational limitations, we couldn't run the algorithm for a large number of generations for all thresholds. It would simply take too long. So we employed an early stopping of sorts, where after a minimum of 250 generations, the algorithm was allowed to stop once it had found a valid solution, where otherwise it would be allowed to run to 2,500 generations. And here we can see that higher thresholds required more generations, and this is expected as we are constraining the optimization to finding only molecules that are similar to the starting one, and also that there's no apparent difference between the multi-objective and the single objective case. Finally, for our last case study, we aimed for a more realistic objective, although it's still quite simple, where we try to optimize for bioactivity towards the dopamine receptor type D2. And this was predicted using a support vector classifier taken from the literature, from the work of Olive Grona et al. And also for non-toxicity. And this was predicted using a multi-target deep neural network, predicting toxicity for 12 endpoints, which was trained on the TOX21 dataset here by us. And finally, also for drug likeness, which would hopefully constrain the algorithm to finding molecules that are sensible, that are not some weird trivial solution like the ones that we are finding for the penalized solubility. So here for this case study, we don't have any baselines from the literature. However, we intended to compare the performance of the multi-objective algorithm that we have been using thus far against two other multi-objective algorithms, namely the strength Pareto evolutionary algorithm 2 and the generalized differential evolution 3. From the top table, we can see that GDE3 found the highest aggregated score, but at the same time, it had the lowest diversity of the solution that it was finding. And it's worth noting here that diversity was not an objective that got optimized. We simply measured it after the fact. Conversely, the single objective genetic algorithm found the lowest score, but the highest diversity. And this goes somewhat against what we were finding thus far. However, if we look at the differences between the genetic algorithm and the NSGA3, which was the algorithm that we are using, we can see that they are slight when compared to the diversity of GDE3. Finally, we also computed some indicators to try and compare the performance of those multi-objective algorithms, and we again can see that the GDE3 mostly outperformed the other algorithms. Then there on the left, we have some examples of the molecules, of the best molecules that each algorithm could find. And we again can see that even though they are exploring the same latent space of the same generative model and using the same objective function, they converge to different solutions, very distinct molecules. And this is a very good trait. So in conclusion, we can see that our method could control abstract chemical properties such as drug likeness, or even more advanced ones like predicted bioactivities, we could mostly outperform or at least match the results from previous work. And then also the multi-objective algorithms often led to more diverse solution sets. And this is particularly interesting as the real-world use case of these kind of methods would be in early drug discovery, where the process is to try to find as many leads as possible, then explore and narrow down to the best one. So with multi-objective algorithms, we could more effectively cover chemical space and find more diverse solutions, different kinds of chemistry that perform the same tasks. And finally, we'd like to point out that our implementation of the similarity constraint likely held back the multi-objective algorithm. So the similarity constraint was implemented in the single objective case as an extra score that got aggregated to the total score. However, for the multi-objective algorithm, it was implemented as a separate objective that got optimized independently. And this allowed the algorithm to focus on regions of chemical space that didn't satisfy the constraints, so that were not similar to the starting molecule. And this then likely led to lower average improvements and to lower success rates. Probably a better implementation would be to simply penalize each of the other objectives instead of optimizing it as a separate objective. Okay. And that concludes my presentation. I hope you found that interesting, and I'm available to answer any questions.
Okay, thank you very much, Tiago. Very nice presentation, very complete set of results. Okay, Bill has a question in the chat. He said, a nice slide, smiles implying chemistry if often cheap. What was 1.5 database? I don't know if you see his question in the chat.
Maybe. Okay, if I interrupt sharing, yeah. So it's question by
Bill London in the chat. The last question.
Yeah, right. So synthesizing a single molecule and testing it is obviously not that expensive. The number that I'm showing is the total cost of the pipeline for developing a new human drug. Yes. But that gives us an idea of how costly some mistakes can be. So if our algorithm suggests a molecule that then turns out to not perform well, this will add to the costs, and those costs are already very, very high.
Can I interrupt?
Yeah.
I think the point is, if you tell people that your solution is going to cost 2.8 billion, that's a totally misleading statement. In practice, if your GA comes up with a SMILES molecule, in reality, most of those are actually going to be synthesizable and at not enormous cost. So you mentioned later on that you were searching for lead chemicals. So if you come up with 100 lead chemicals, they're not all going to cost 2.8 billion. And in practice, what you're interested in is novel chemistry. And so having a technique that can generate novel SMILES forms will lead you to novel chemistry at significantly less cost. The other thing I wanted to say was, I think it's very nice that you actually put the chemical formulas on your slides, because in practice, that's what the chemists are going to recognize, and saying your fitness is 1.7% better than some other guys, they don't care. But if you put it on the slide, a molecule that they can look and understand, then that's a very good way of selling your work. Whereas fitness functions, they don't care about.
Yeah, exactly. So for the first point, I was trying just to give some context to the drug development pipeline, and not directly to the costs associated with this. So try to give a perspective of why these methods are important, and what we are trying to achieve actually is bring down that cost. So try to find a better process, try to find more useful leads that waste less resources in exploring them. Yeah. And I also agree with you that showing molecules is much more appealing than showing some fitnesses. Yeah.
And earlier on, you mentioned a 1.5 million chemical database, but I didn't get what that was or what the characteristics of those molecules were.
Yeah. So that's a subset of the Campbell dataset. The Campbell.
Okay, I've not come across it. Okay.
Campbell.
It's in the paper, I assume.
Yeah. It's a common dataset. It's mostly drug-like molecules. However, we filter it down for removing salts and some other molecules. That exact dataset was the one also used in the paper that suggested the architecture. So I can.
No, if it's in the paper, that's fine.
Yeah, it's in the paper.
Okay, thank you.